Hey Adam, welcome to the future of testing.
Hey, nice to be here. How are you
Great to
doing, Joe?
Good, great to see you again. The floor is all yours, so it's all up to you.
Awesome. Next generation functional testing using visual AI. So, it's not a secret that many teams struggle with automated functional UI testing, some to the point where it is completely abandoned, despite the fact that the UI is the most important interface of the system. Even teams that experience initial success soon find themselves unable to retain high test coverage as the overhead of maintaining existing tests and analyzing test results increases over time. In this session, we will introduce a new technique for implementing automated functional tests that eliminates most of the downsides of the traditional approach. This technique is based on visual AI, which is the advanced computer vision technology that powers our visual testing service, and it has been successfully used for several years by our own R&D team at Applitools, and also by hundreds of other teams around the world, and I'm sure you'll find it very useful as well. So let's start by reviewing some of the challenges the team experienced with the traditional approach to functional test automation. In this session, I'll focus on end-to-end functional UI testing, despite the fact that visual AI applies to many other forms of testing, component testing, localization testing, accessibility, responsive web design, and many others. And when we're talking about end-to-end functional UI testing, we're talking about testing the end-to-end functionality of the system through its UI. It's the most widespread type of functional testing. This is the type of testing that you do, automate with tools like Selenium, Appium, Cypress, Playwright, and dozens of other excellent tools. And just to make sure that we are on the same page, every test consists of a sequence of steps in which you first simulate some user inputs by navigating, moving the mouse, clicking, typing data, and then validating the system output using assertions. Now, also, I'm sure that we all know and agree that end-to-end testing is critically important, because even if you have excellent components that function very well on their own, if you don't put them right together, integrate them together, and they don't work correctly together, you might end up with a suboptimal system that no one would like to use. So let's take a look at a very simple end-to-end test that probably almost every company in the world needs to automate. We want to make sure that if a user tries to log into our system without providing the username and password, he is introduced with error messages that indicate that those fields are required. Very simple. Here's how we would implement such a UI test with Cypress. Don't worry if you don't know Cypress. It's very similar to any other framework and very easy to read. In line 3, we visit the login page. In line 5 and 6, we click the login button. And in lines 8 to 17, we perform a few assertions that basically locate the error elements on the DOM and make sure that they have the correct text on them. And then you try to click the login button again to make sure that it is still usable. So a very simple implementation to test this functionality. Now, what would happen if another developer on our team, or in a different team for that matter, alters the CSS of this application to change something else on a different part of the application and accidentally modifies our sign-in button? Okay, so as you can see, it's narrower, and it's now green, the text is black instead of white, it's not capitalized, etc. This is what we would call a visual bug. We call it a visual bug because visually the button looks different. However, in terms of functionality, it still works. I can still click it and log in. And as far as our test is concerned, the functionality is still working. Of course, our test will not catch that. It will still pass, but it wasn't intended to catch that anyway. But what would happen if that same change actually changed the color of the error message from red to white? In this case, the error messages would be white text on white background, and they would practically be invisible to the user. This is now a functional bug because the core functionality that we are trying to validate no longer works. The user does not see any error message. The annoying thing is, even in this case, our functional test is still passing because there are still two DOM elements with the error messages, and they still have the text, the correct text in them. Now, this was a very simple example. Most applications have more complicated screens with a lot more elements, with hundreds of elements that needs to be validated. Let's take a look at this real-life example. You can see that there are many elements here, and it would take dozens, if not hundreds, of lines of assertion code just to validate the full state, single state of the application. I'm not even talking about the graphs and the charts, just the DOM elements that you can assert on. And what happens when the UI changes? The same people that are responsible for implementing the test would have to stop what they're doing and start analyzing what happened. They need to look at the test results, at the system logs, and figure out if the bug is in the application or the test is broken. And if the test is broken, they need to basically fix it, correct the code. Now, this creates a huge bottleneck. And what we see is that teams spend anytime between 40 to 70% of their time analyzing test results and maintaining tests once they have a mature and large test suite. And this is, of course, prevents them from working on adding more test coverage for new product features. And this creates a big coverage gap. So the reality of end-to-end testing, UI testing for that matter, is that it's extremely painful. And most teams experience that. Basically, every assertion that you add to your test increases the maintenance overhead, and teams start to question, is it worth it? Maybe we're better off not testing this automatically. Maybe we should test it manually. Maybe there's not a big risk for this bug to happen. You just can't afford to automate everything. The fact that you need coding skills to analyze the logs and then fix the test creates a big bottleneck because there are very few people in the team that can actually do this maintenance work. The fact that you can assert on non-DOM elements such as images, Canvas, CSS, graphic, and many other exotic technologies further increases that gap. You get relatively low coverage from your test because you're restricted with those assertions to test the functionality of the application. You cannot validate the UI itself, which is a very important UI. That's all the visual testing part. And the other part of it that you can only catch expected bugs. Like we saw with our example, the test would fail only if the text of the error messages would change, or if the error messages, there won't be two. However, there could be 1,000 other ways that we can think of that the functionality will break and the test won't fail. It means that our test is not catching unexpected failures. At the bottom line of all of this is that most teams experience low test coverage, and they have to compensate for it by manual regression testing, whether they call it exploratory testing or they just have manual regression testing. They have to do it, and it's very common that we see companies that have a few or maybe a dozen test automation engineers responsible for automating tests, and they have hundreds of manual testers that do all the rest, right? Everything that is not covered by those tests. The solution and alternative that I would like to propose here is automating your UI test with visual AI. And the way that you do it with Applitools is that we provide you with an SDK that you integrate inside your existing test suite, no matter what platform or programming language it's written in. And it allows you to add a single visual checkpoint that can replace all those traditional assertions that you have. And what this single checkpoint does is that it grabs a screenshot of the entire page, not just the part that is visible in the browser viewport or on the device viewport, the full page, sends it to our server for analysis, where it gets compared with the baseline image that defines the expected appearance of the application at this point in the test. If there is anything different between the two, this visual assertion will fail. It will throw an exception that will fail your test. And inside that exception, there will be a link to our dashboard where everyone can clearly see what changed. What is the change as the user, the end user would see it between the baseline image and the checkpoint image. And all you need to do at this point to maintain your test is just decide if this change is valid, you expected it, or if it is a bug. It wasn't expected, in which case, if it's valid change, you accept the new screenshot and it becomes a baseline image for subsequent test runs. And if it's an invalid, it's not an expected change, it's a bug, you reject the new screenshot and report a bug. We have a built-in bug reporting system, and it also integrates with Jira, etc. So basically, you don't need to touch or change the test code. Visual assertions have many advantages over the traditional assertions. The first is that a single visual assertion gives you complete visual and functional coverage for the page and replaces having to write and later maintain hundreds of equivalent lines of assertion code. The second advantage is that when the UI changes, this line of code doesn't break. It doesn't have any locators in it. It does an implicit check for the entire page. All you need to do is go to the UI, accept or reject the change. It means that you no longer need to spend time in those logs. You no longer need those specific people to go into the test, have coding skills, and fix this. The fact that no coding skills required to maintain those baselines and maintain those test results means that everyone in the team can participate in the test maintenance, and this has the potential to open up a huge bottleneck. The people with the coding skills can continue and implement more and more tests and keep test coverage high, where everyone in the team, even non-coders, can actually do the maintenance and see what is changing in the application, approve or reject it. Another big advantage of this approach is that it allows you to get a lot more out of your existing test. Because we compare the entire page with the baseline and let you know if anything is different, you'll start finding unexpected issues from your existing test, which will really increase the amount of value, the return on investment that you get out of your automating test in orders of magnitude. And again, I'd like to emphasize that you can integrate visual assertions with just about any programming language, any test automation framework, any UI technology, or application technology, whether it's web, mobile, iOS, Android, just screenshot, anything that you do, you can have visual testing, visual validations added to it. Now, I'd like to support my claims with some empirical data that was collected from the 288 completions of the Applitools Visual AI Rockstar Hackathon that we conducted earlier this year. In this hackathon, we asked a group of test automation professionals to implement a set of UI tests for buggy web applications, first using the traditional approach and then using Visual AI. Here are the results that were found. First of all, the time it took to implement the test suite was 6 times faster with Visual AI than with the traditional approach, and it was also almost 8 times faster for the 10 best completions, for the 10 winners. In terms of total lines of code, it took 50% less code for using Visual AI and 72% less code for the winners. In terms of number of locators, we can think of it as the amount, the capacity in the test that determines the amount of maintenance required later on. So it took 80% fewer locators with Visual AI and 95% fewer locators for the winners. And the bottom line, in terms of the coverage gained, then participant got to 95% coverage with Visual AI compared to 65% with the traditional approach and 100% coverage for the winners. Now, I think that these results are quite amazing and they really show the advantages of Visual AI. But what's more amazing about them is the fact that, first of all, you can see that there isn't a big difference between the overall participants that completed the hackathon and the 10 best participants. This implies that everyone can succeed with this technology. It's easy to use. It's easy to get value out of it. You don't have to be like the smartest developer in the company to do that. Second, think of these participants. These are test automation professionals with years of experience working with a traditional way of testing. And it was the first time that they ever saw or used Visual AI. Just think of these results, of the differences we would see if they would also have the same amount of experience, of years of experience using Visual AI. So to conclude this section, from what we see over the years with hundreds of teams, is that anything that you can do with traditional UI testing techniques, you can accomplish with visual AI, and you get much, much more coverage, and it takes a fraction of the effort to create tests and maintain them moving forward. We also see that if there are things in those tests that you cannot accomplish with visual AI, in most cases, these are example of situations where people are doing in their UI test things that were better off being done at the API testing level or at the unit testing level. Okay, so of course, in order for all of this magic to work, it has to be super robust and accurate. Otherwise, teams that are running tens of thousands of tests every day would experience a lot of false positives, failures, and won't be able to succeed. So although we are not 100% accurate, today we have one false positive out of 1 million checkpoints, which is very, very accurate, and we are continuing to work and improve that all the time. If we look at what we do in terms of AI at Applitools, then basically we have what we call visual AI is basically a code name for dozens of computer vision algorithms that focus in two areas. The first area is being able to compare screenshot just like a human would. And there's a large spectrum of options here. On one hand is being able to ignore slight rendering differences that occur when you render the same screen with slightly dynamic data or a different screen or different hardware, or where things, when the layout engine of browsers shifts things around a bit. So there can be substantial pixel differences. They are invisible to the human eye, and you need algorithms that are able to understand how the human eye works and how people see things in order to ignore them. I'll show you some examples soon. But on the other hand, being able to handle extreme dynamic data, such as think of complex retail sites with dynamic content and products that change according to what's available in the inventory, where there are new deals and offers that pop and change according to the time of day or the person that is coming in and watching the website. A lot of pattern detection, the ability to handle all these variances on the page. The algorithms can handle this type of challenges as well. The other area of focus is being able to eliminate repetitive maintenance tasks. So just to give an example, if we detect a difference like we saw in the example, our AI is unable to decide if it's a bug or not a bug. The reason it's unable to do it is because even people cannot decide between themselves. I constantly see my developers, my product guys arguing among themselves if a change looks good enough or not. So a machine won't be able to make this call better than they do. However, once it introduces this change and a qualified person that knows the product gave the subjective feedback that it is okay or that it should be rejected, at this point, we can have algorithms kick in and make sure that in the 200 other places in the product where the same change appears, different pages, different devices, browsers, operating systems, etc., you can apply the same feedback and you don't need to ask it over again and again. Okay, so there are many features in the product that actually go and automate these this dirty work for you, and I'll explain a few more others later on. So in order to accomplish all of this, we have many algorithms that that we take different approaches to develop. Many of them are rule-based or hand-coded algorithms. Many of them are based on classic machine learning tools, and some are based on deep learning. Now let's take a look at some of the challenges that we need to cope with. The first one is an example of cases where there are rendering differences that are invisible to the human eye. You can see at the bottom of the screen, there is a navigation bar with a playlist tab. You can see the playlist text, which is white. If you would look at the DOM, you see that the text is white. But if you look at the magnified pixels, as they get rendered on the same computer with two different screens connected to it, you can see that the pixels can come out very different. You can see that one has pixels in shades of pink and the other has only shades of blue, right? Now, a lot of the pixels are different. However, on the playlist tab, it looks exactly the same because our eye doesn't see it from at this size. So you need very sophisticated models and algorithms that can understand that all these pixels are basically, pixel changes are invisible. But on the other hand, if a plus symbol changes to a minus or a comma changes to a period, that could be just a 4-pixel difference. We should still understand that a human being can see it, that it is a substantial difference, and highlight it without making a mistake. Here you can see an example of comparing screenshots taken on different devices. So checkpoint image on Google Nexus 5, baseline image on Google Nexus 4. The form factors are different, and because of that, the text and the image sizes, we can understand it and still see that the logo moved at the top and indicate that there's a structural change, but ignore all those other changes that are basically maintain the structure according to the form factor. Okay, so a deep understanding of the structure of the page by analyzing the image. Another example, also of automated maintenance, when you change your UI, which you of course do all the time, things shift around. Maybe you added a new element, you change the padding or margins of element. Then at this point, there will be a substantial change on the page. However, and it's very easy to make a mistake and see the change and say, yeah, I know that we changed it, so it makes sense that everything moved. But beyond this change, there could be another thing. You can see in this case that the text has changed as well. Visual AI will actually tell you that it identifies that things shifted, but there is other content there, and ask you if you would like to ignore the shift so you don't miss that out. Okay, and this way it helps you quickly do the maintenance without missing important changes that happened. Another example of automated maintenance in action. In this case, we have 76 differences across a test suite that ran on different browsers, devices, and operating system. Instead of looking at 76 differences one by one, you can ask the tool to actually group steps by similar differences. After a few seconds, there are only 2 unique differences that just repeat across those 76 occurrences. And you just have 2 images to look at, and there you go. Instead of spending an hour maintaining, you're done with 2 clicks. Okay, so it's features like that that really go a long way in allowing you to scale your test, write more and more tests, run more tests without really increasing the maintenance overhead. Another very powerful feature is root cause analysis, where for web applications, we allow the developer to see not just what the visual difference is or what is the difference between the baseline and the checkpoint image, but also to see what change in the code that caused this difference. The way that it works is that when we take the screenshots of the checkpoint images, we also capture the DOM and CSS. And when the screenshot is saved as a baseline, this is stored along with the baseline. So when we have a visual difference, we have algorithms that analyze the differences in the DOM and CSS of the 2 images and come up with a suggestion of the root cause for that change. Now, it goes far beyond just telling you that the color of the button changed from green to blue, which is useless because you can see that in the image. It actually shows you which parent container had a class removed, CSS class removed or added, and as a result, which CSS rules were applied or removed. Now, this can be very helpful because in many cases, a change like this doesn't happen because a developer did a mistake directly in the page that he built. Usually this happens when another developer changed something else in the application and accidentally affected this page. So it helps the person responsible for this page to understand what really happened. And there are other situations where this can save hours of work. For example, if to reproduce the problem, you need special data, or it reproduces once in 10 runs because it's like a flaky bug, a race condition, or something like that. In this case, if the bug happened, you have all the information. It also empowers QA engineers to just report bugs that automatically have a lot more important information that otherwise they would not be able to gather. Now, I want to emphasize and clarify again that the examples that I've shown you up to this point, we saw code with Cypress, we talked about web applications. This technology, Visual AI, applies to basically every type of UI you can think of, from web to mobile to checking documents, PDFs, any image that you can come up with, we can test. We have SDKs that target manual testers, that target developers, that target test automation engineers across all the different platforms, all the different test automation frameworks. And whenever a new one comes out, we immediately support it. This means that it doesn't matter how diverse the tech stack in your company is, how many teams there are, and what the different tools they use to test and develop. They can use Applitool, one of Applitool's SDK to work with, and this technology applies to them as well. This also means that if you are migrating from one framework to another, to the next shiny thing, or of course, if you are migrating or rewriting the UI of your application, by using Visual AI, you have much less work to do in migrating because there is a lot less code to move. Needless to say, of course, there are also integration with all the CI tools, CI/CD tools, and the CSM systems such as GitHub, GitLab, Bitbucket, and the rest of them that make it very easy and seamless to integrate visual testing and the test analysis and all of that directly in the normal workflows that you have today. So to the last part of now every team that has a test suite, the next thing they want to do is run it on the same devices and browsers that their customers are using to work with their application. And of course, they want these tests to run very fast, stable, and at scale. One of the very important advantages of using Visual AI to implement your functional tests is that if you do that, you can also execute those tests on different devices and browsers and operating systems using the Applitools Ultrafast Grid. Now, the Applitools Ultrafast Grid is not your usual grid. It is far more modern and advanced, and it works very differently from the grids you are used to. If we take a traditional grid, let's say you have 1,000 tests, and now you want to test it on 20 different browsers and devices. Basically, what you need to do is run each test 20 times. You need to alter your test framework to do that. And it means that instead of running 1,000 tests, you're now running 20,000 tests. It means that you have 20 times the test results to wait for, to analyze. If there is a bug, it appears 20 times on the different clients. Because the browsers would reside in some grid, remote grid, and every interaction with the browser means an HTTP request that goes to the other end of the world and other side of the world, and this means flakiness and slowness. It also means that somewhere there is a device that needs to be up for the whole duration of the test, and that's a long time, and things can go wrong, and they do. In general, nobody really loves doing this process. The Ultrafast Grid takes a different approach. Basically, what we do is that when you have a visual checkpoint, instead of grabbing a screenshot, we actually extract all the resources from the browser that are used to show the current state of the application. Anything the browser is using to render the page as you see it. This includes fonts, DOM, CSS, resources, images, everything. It then uploads all the new resources it encounters. If it already uploaded the font in the previous test run or in another test, it doesn't need to upload it again. The grid already knows that font. Okay, so it only uploads the deltas, which there are very few of them normally, and a list of devices and browsers you want to test on. What the grid does then is within seconds, it spawns up all those devices and browsers, injects the resources of the page you want to check into them, and produces a full page screenshot in each of these devices and generates a visual test for you. The end result is that at the same time it takes you today to run your 1,000 tests, you get the coverage with Visual AI, with all the advantages that I explained before, of 20,000 tests. Okay, and the beauty is that it's so simple to add. You don't need to alter your test framework at all. All you need to do is just specify a list of devices and browsers. Let's see this in action. What I'm going to do is that we're going to run a test that navigates to wikipedia.org, searches for the functional testing article, and validates the whole page. Okay, and we'll do it on 15 different devices and browsers. You can see that there are plenty of elements here. We'll have 100% coverage for this test on all those devices and browsers. The way that we'll do it is using Playwright, which is a new framework by Microsoft. You probably heard about it. So there's some boilerplate code with Mocha, but it's not interesting. What's interesting is that we have the list of browsers that we want to test on, a variety of them, some mobile-based, some desktop-based. And the test itself, we start by notifying the eyes server that we are starting a test with eyes open. We indicate the name of the application, Wikipedia, and the name of the test, functional testing. Then we just go through with the simulating the user inputs. We navigate to wikipedia.org. We type functional testing in the search input, and we click the search button. Then when we get there, we do a visual checkpoint, just like we saw in the example before. This will take care of a full coverage for that page, and we let the server know that our test is over. Okay, very, very simple. Let's run this test and see what we get. So, as you can see, Chrome is starting just one instance, navigating to wikipedia.org and searching for the functional testing article. And now we wait. What happens now is that the SDK has extracted the resources, uploading them to the Ultrafast grid, providing the same list of devices and browsers that we've seen before. The grid is now spawning all those devices and browsers, injecting the test into them, and generating the test results. We are done. You can see that it took exactly 25 seconds. This is super fast, and if you have any experience with cross-browser device testing. And if we go back to the eyes dashboard and refresh, you can see the test that we just ran with 15 past tests. They cover the different operating systems and different devices that we specified. And if we look at the checkpoints, you can see that each checkpoint covers the page on the specific device. If we look closer, you can see that there is a checkpoint image compared with the baseline image that includes every detail of that page. So if anything would change, you will know about it. That's 100% coverage for that page. I think this is pretty cool and amazing every time I do it. Okay, so let's talk about the advantages of the Ultrafast grid. First of all, it covers all the environments at the speed of running a single local test, which is phenomenal. It is also much more robust, stable, and fast than running 20 times the same test and interacting and doing the full scenario in each one of them. When you use the Ultrafast grid, you get full functional visual coverage with visual AI, including all the benefits of visual AI that I mentioned before in terms of the increased coverage, less maintenance work, automated maintenance, all of that. In addition, because you run only 1,000 tests instead of 20,000 tests, you spend less time setting up test data, data preparation, cleaning up databases, setting up the environment, provisioning users. There are less tests running at the end of the day. The tests themselves are also simpler. If you have a responsive website, it would look different on different devices. So you need to adjust your tests to accommodate for those differences so you can actually go through the entire scenarios on each of these devices. With Ultrafast grid, it just runs once. It doesn't matter on which form factor. Once we've done that, we have all the resources, and with just a simple run for one of the different layouts of the application, you get coverage for all. It is also a very secure solution. The SDK resides inside your tests behind the company firewall. It extracts the pages that you wanted to, and it sends them outside to the eyes server. Or if you are worried about data, then we can also install on-prem behind the company firewall. And there is no inbound access required from our servers to the application that resides behind your firewall. This is in contrast to the traditional grids that have browsers that need access to the application behind your firewall. It means that you either need to use tunnels or open up inbound access in the VPNs, and this compromises the security of the company. And last but not least is that the solution is very developer friendly. You don't need to make changes to your test framework and write a lot of code to facilitate running across different devices and browsers. As you saw in the test, all you need to do is provide that list of devices and browsers, and you're done. You get the ultra-fast grid to run those tests for you. So to conclude the session, before we move on to answer questions, doing functional testing with visual AI and the ultra-fast grid drastically increases the test coverage and allows you to start finding unexpected issues with your test automation. It drastically reduces the time it takes you to create and maintain tests. It drastically reduces the time it takes you to execute the test using the ultra-fast grid, and also analyzing test results using automated maintenance features, as well as the fact that you don't need to look at logs and it's all visual and clear. It supports any framework that you're using today or will use tomorrow. And of course, it's important because the grid is so efficient and easier and cost less for us to operate, it also costs a lot less for you. So you can really cut down on those test lab costs by moving into that grid, in addition to the benefits that it will provide. So thank you very much. And I'll be happy to take your questions.
Another great session, Adam. Thank you so much. So we have a few questions coming in. The first one is from Vicus. He wants to know, primarily the web pages have data, say in the form of tables, which are dynamic. Say a page search on laptop on Amazon. How can this tool help in those cases where the values next day will be different?
Excellent question. So in general, part of the testability of any application is the ability to generate mock data for it. So if you take, for example, a newspaper, right? And we have many customers in the media vertical. So of course, they can test, they can decide to monitor the pages in production and make sure that there is an article there. There can be a different title, there can be a different body for the article, there should be 3 columns on an image. They can make sure that structurally this happens, this exists, and they can use our algorithms to do that. But before releasing a new version, they can actually use the same test article and make sure that it looks exactly the same. This means that every pixel, everything that should be, does appear in the right color, test a color, shape, and size, right? They can get and make sure that this article as an example article, or choose 10 example articles, are exactly as they're supposed to see it. So it's a combination. The more control you have over the data, that's usually something that you can have pre-production, you get more coverage. But you can also use structural matching, just like you saw with the example of comparing the 2 screenshots on different mobile devices. You can still structurally make sure that the product list, there are still products there, that the pattern of the product repeats itself. If there is a table, you can make sure that there, let's say in the baseline, there are no empty rows. The algorithm will identify that there are no empty rows in the other table, even if there are more rows. If the text has a certain size, it is aligned to certain areas. Do you allow certain cells to be empty? Okay, so the algorithms are very smart, and they can infer a lot of data from the baselines and make sure that it applies to the checkpoint image, even if the data is extremely dynamic. Now, clearly, if you are testing in production with dynamic data, then you can have typos or nonsensical data there. It won't be able to capture it because it does not conform to the baseline in any way. However, if you do have the ability pre-production to control the data, that is very useful, and you get the full coverage that I mentioned.
Great. So Adam, another question. This is on speed. I think these people are going to be pleasantly surprised, but let's get your opinion here. They want to know, what is the impact on test execution time when using Applitools, since the screenshots are sent to the server that's processing, etc.? Does it make the test run slower if I were to run the visual test in a functional way? How much slower, and how do we deal with this?
So first of all, as you saw, it's much faster if you're using the ultrafast grid. Like not much faster, it's much faster. Okay, let's start with this, and more stable. But let's assume that you don't, let's put the ultrafast grid aside. Let's assume you decide not to use it for some reason. Then correct, we need to capture a full page screenshot, and we need to upload it to the servers. And this adds overhead. It doesn't add a lot of overhead. The screenshot analysis is very fast, depending on the size of the page, like a very large page, depending on the algorithms that are being applied, but it can take between tens of milliseconds to a second to process. It's not too much of a big deal. It does take time if you're not working on the grid to scroll the page and produce the full page screenshot, and especially if you're working on a mobile device, a native application. These frameworks are very slow. Appium, you probably know, it's very slow, so it does add overhead. However, it depends what you compare it with. So let's say you're doing functional testing today. Of course, you're not testing the visual parts of the application, right? So you are spending hours and hours of work, manual work, to test the application in other ways. If you use Applitools, you don't need to do that, right? So you basically, your automated tests take a bit longer to run, but it's still 100 times faster and 100% accurate than doing manual testing for the same purposes, right? So it does save you a lot of time if you look at the overall coverage gain that you get. If you're just comparing a lot of coverage compared to almost no coverage, then you get almost no coverage faster. But then again, with the ultrafast grid, we are much faster as well with all that extra coverage.
Great answer. Another question. This is actually from Ricky. He put it in the chat here. How does this handle different graphical elements being displayed on different test systems, like your local laptop versus a virtual machine?
So these are basically, this is the secret sauce. This is what we've been working on all along. So our algorithms are actually tuned to do exactly that. We are able to ignore all those differences very effectively with very high accuracies. For example, the example that I've shown you with the changing pixels, things that happen all the time when you have different testing systems, then you'll never get a false positive like that. Ever, never, ever. I mean, this is something that is so accurate today after years and years and years of developing and refining these algorithms, and thousands, tens of thousands of customers that have been working with this for years. At this point, you will almost never see any issue at all.
Absolutely. And as a customer, I've never seen an issue either. So it's an awesome solution. So thank you for it, Adam. Before we go, any parting words of wisdom you want to leave the future of testing?
Yep. So first of all, what I've shown you now is how my team is testing the product itself. Okay. They have the liberty of doing and using any other tool and any other technique that they want. No one is forcing them to do it. I know for a fact from my own experience how effective this is. I know it from the experience of the many, many customers that we have that use the product over years and just increase usage. This is a real game changer, and I really encourage you to try it out. It's really, really, really as amazing as I'm trying it to sound like, and you should try it for yourself.
Great words of wisdom. Thank you so much, Adam. Really appreciate it. Cheers.
Thank you, Joe.
Thank you.
Okay.